Which of these terms is another name for voltage? So remember, the voltage is the height of a hill that a charged particle rolls down. Is it electric potential, electric field strength, electric flux density, or potential difference? Let's go through our options. Electric potential is like the absolute height of a hill, but it's not the distance that the charged particle will roll down. If the charged particle goes from a higher potential to a lower potential, we still don't know the absolute values of those potentials. So that is not the voltage. Could it be electric field strength? Well, no, this is something quite different. Electric field strength is measured in volts per meter, and voltage is measured in volts. Electric flux density is just another measurement for electric field strength. It's technically a measure of how close together the electric field lines are. The last option is potential difference, and this is the correct answer. So voltage is the difference between a region of higher potential and a region of lower potential. At a high potential, a positively charged particle will have more potential energy, and at a low potential, the positively charged particle will have less potential. So it tries to roll downhill from the high potential to the low potential. Question 17. Two oppositely charged parallel plates form a uniform electric field. If they are 2 centimeters apart and the field strength between them is 75 volts per meter, what is the potential difference between the surfaces of these plates? Well, here we're going to need an equation relating voltage to distance and electric field strength. This is why it's useful to measure electric field strength in volts per meter. So the potential difference between 2 points in a uniform electric field is voltage equals electric field strength times distance. So if we mark 2 points in an electric field, the distance between them multiplied by the electric field strength tells us the voltage between those 2 points. So substituting in the numbers, we have 75 for the electric field strength, 0.02 centimeters, because that's how far apart the plates are, and we want the voltage between one plate and the other. And that gives us 1.5 volts between the plates. Question 18. If a positive particle and a negative particle are placed very close to a stationary negatively charged plate, which one has more potential energy? Justify your answer. So let's draw a diagram so we can visualize this. We have a plate that's negatively charged. We have a negatively charged particle and a positively charged particle right next to it. So the question is, what's going to happen when we release each particle? The positively charged particle will move just a tiny bit because it's attracted to the negative plate and stop. So it wouldn't really have much potential energy. But the top particle, as soon as we release it, it's going to go flying away from the negative plate because these are repelling each other. So this means that this has a lot of potential energy. It has the potential to fly away from this negative plate. So that's what we have to write down when we answer this question. The negative particle has more potential energy because it has the potential to be repelled a very long way. On the other hand, the positively charged particle has much less potential energy because it will not move very far at all when it is released. Question 19. An electron passes through a voltage of magnitude 2000 volts. How does its potential energy change? The amounts of energy that we change here will be the same as the amount of energy it would take to pull the electron back and put it back where it was. So, how do we relate energy to voltage and charge? Well, we use the equation work, that is, the potential energy that we've lost, equals QV. So the energy gained by a charged particle depends on its own charge and the strength of the electric field. The work done on the particle in order to move it back up is work equals QV. So substituting in our numbers, we simply have the elementary charge times the voltage it's moved through, which is 3.2 times 10 to the minus 16 joules. Now, is it gaining potential energy or is it losing potential energy? Well, all we're told is that the electron passes through the voltage. We don't know whether it's being pushed uphill or whether it's rolling downhill. So the electron's energy changes by exactly this amount, but we don't know whether it's increasing or decreasing without knowing which direction it's passing. If it's going towards the negative plate, then it's gaining potential energy because it's getting more and more potential to fly away from that plate. If it's moving toward a positive plate, then it's going to be losing potential energy because the closer it is to the positive plate, the less it will be able to fall towards the positive plate. Question 20. By convention, when drawing electrical circuits, physicists draw the current flowing from high potential to low potential. So if we have a little hill, this is a high potential, and this is a low potential, we say that the particles are moving like this. So this is how we draw the current flowing from high potential to low potential, the same way that positively charged particles would move, right? Is this a good representation of the underlying physics? Explain why or why not. To answer this question, we have to think back to how electric charges work. Now, electric charges arise when we have either too many electrons or too few electrons. In either case, the protons don't do any moving, it's only the electrons. So when electricity flows, the protons, the positive charges, actually have nothing to do with it. The electrons are what move, and they move in the opposite direction. That is, they go from the potential that we call low to the potential that we call high. Even though at low potentials, the electrons have a large amount of potential energy, and at high potentials, the electrons have a low amount of potential energy, which is exactly the opposite to what the positively charged particles do. So ignoring the positively charged particles, because we don't get those for electricity flow, the direction that we draw the current is the opposite of the direction that we draw the electron's motion. So our answer here is going to be something like this. Electric current is a measure of electron flow in a circuit, and the electrons flow against the direction of the electric field. They go from low potentials to high potentials, and not the other way around, like a positive charge would. So this means that the direction of current is opposite to the direction of the actual movement of the electrons, and it's not a good representation of how the world actually works. So that's the end of the questions, which means that we're at the end of the section. So in this section, we've learned about electric fields and how they affect the energy of particles passing through them. If we mark 2 points in an electric field, we can calculate the voltage between them, which is like the height of a hill that the charged particle can roll down.